This is Module 6, Investigation 2, End Behavior of Rational Functions. Recall the following context from Worksheet 1 of this module, so Investigation 1. The cost for a jet fuel company to supply jet fuel is $3.90 per gallon of fuel. Also, the jet fuel company has an initial cost of $3,200,000 to purchase the tanks to store the fuel. In the previous worksheet, we defined the relationship between the cost of C of supplying jet fuel and the number of gallons supplied X by C equals F of X equals 3,200,000 plus 390X. We also defined the relationship between the average cost per gallon A and the number of gallons of fuel supplied X by A equals G of X equals F of X over X equals 3,200,000 plus 390X over X. So we have a rational function here, a polynomial function which is linear in the numerator divided by another linear function in the denominator. Use the following table to determine the average cost per gallon to supply the corresponding number of gallons of fuel. So for each of these, we just need to plug or substitute 1,000 in for X into our function. Let's see, two functions. One, F of X for this column, and then G of X for this column. So for the first one, F of 1,000 equals 3,200,000 plus 390 times 1,000. That is quite a big number, 320,390. 3,203,900. Then the average cost, G of X, is just that number divided by X. 3,203,900 divided by 1,000, which is 3,203.90. And now we can fill out the rest of the table in the same way. So as the number of gallons of fuel supplied increases, how does the average cost per gallon of fuel change? We can see that it's decreasing here. What is the change in the average cost per gallon as the number of gallons of fuel supplied increases from 1 million, which we have right here, to 20 million, which we don't have on our chart, but we can find the change. The change will be whatever the value is at 20,000, which we can just find by plugging that into the function G. 20 million, I'm sorry. And we get 406. So the final average cost minus the initial average cost, which was 710, which is negative 304. So the average cost decreased by $3.04 as the number of gallons of fuel increased from 1 million to 20 million. What value does the output of G approach as the number of gallons supplied increases without bound? What does this information convey about the covariation of quantities in the context of the problem? So what does the value of G approach as X increases without bound? Well, let's do one more really big value of X, like G of 999. As big as you can think of. Let's see what happens if we plug that into our calculator. So if you plug that into the function G, which is the function f divided by x, we get 3.90032. Now notice that this was at 3.93. What's going to happen if you plug larger and larger numbers, your numbers are going to get closer and closer to 3.9. So as the number of gallons increases without bound, the average cost approaches $3.90. You could even look on your calculator and see that if you just keep scrolling to the right forever, the output gets closer and closer to 3.90. And that's actually what we call a horizontal asymptote. There's a horizontal asymptote at y equals 3.90. So even the function approaches 390, the output will never quite reach it. So part E says, if the number of gallons of fuel supplied by the jet fuel company continues to increase, will the average cost per gallon reach a minimum value? The answer is no, although the cost gets closer and closer to 390. It will never reach that value, and we can always get a little bit closer. Recall the following context from worksheet 1 of this module. 5 gallons of liquid flavoring is poured into a large vat. Water will be added to the vat and mixed with the flavoring to produce a drink that will be bottled and sold. We defined a function to relate the ratio of flavoring to water R in the mixture to the total volume of the mixture X in gallons by R equals f of X equals 5 over X minus 5. What happens to the ratio of flavoring to water as X gets larger and larger, that is, as X increases without bound? So right away, I know the answer to this one is the ratio of the flavoring approaches 0. Think about this. As X gets larger and larger, we'll have like 5 over, like if X equals 10, it'll be 5 over 5, which is 1. If X was 100, we'll have 5 over 95, which is a pretty small fraction. 1 over 19. As X grows larger and larger, that denominator gets larger and larger, so we get a smaller and smaller fraction. If I use 1,000 for X, then we'll have 5 over 1, or 9995, which is 1 over 199. This ratio gets smaller and smaller, approaching 0 as X gets larger and larger. That means that there is a vertical or a horizontal asymptote at y equals 0. Really, it's r equals 0. Is there a minimum value for r? If so, state it. If not, explain your reasoning. Not quite, because this ratio, although it'll get smaller and smaller, it'll never be quite 0. We're always going to have a 5 in the numerator. We'll have 5 divided by some really big number. We're going to get closer and closer to 0, but we'll never quite reach 0. So it'll just keep getting smaller. We can't get a minimum because we could always might find a number smaller than the one that we picked. And it'll never quite be 0. Use the calculator to graph f. How does the graph support your findings in this problem? So, should have a graph kind of like this. Notice there's our vertical asymptote at x equals 5, like we looked at in investigation 1. And notice as x gets larger and larger and larger, the output gets closer and closer to 0. There's our horizontal asymptote. At y equals 0. Now technically, our function wouldn't really even have this piece of the graph over here if we're talking about the context of the problem. We can't have a total volume less than 5 since we already have 5 gallons of flavoring in the vat. So the graph shows that as x gets larger and larger and larger, the output gets closer and closer to 0, and it never quite gets there. If you just scroll to the right on your graph trace, you'll see that the output y value gets smaller and smaller and smaller, but never reaches the axis y equals 0. Number 3, a national park research team noticed a dramatic reduction in the deer population in a 150,000 acre protected area. In order to increase the population of deer, the Park Services introduced 125 additional deer into the area. The researchers' population model predicts that after this, the expected number of deer n will be described by the function n equals f of t equals 50 times 2t plus 16 over 0.0075t plus 4, where t is the time measured in years since the 125 deer were introduced. And here we have a rational function, one polynomial function divided by another, and they both happen to be linear. What was the deer population previous to the addition of the 125 deer? Explain how you determined this value. Well, if we look at t equals 0, that's the time since the 125 deer were introduced. If we find that population, then we can subtract 125 to find out how many deer there were before they were introduced. So f of 0 minus 125 is going to give us our result. Now if you plug 0 into the function, you should get 50 times 0 plus 16 is 16, divided by 0 plus 4 is 4, which is 50 times 4, which is 200. And then we want to subtract 125. Really, I should have put, to keep my equality, I need to subtract that 125 at each place here. 200 minus 125 is 75. Find the population when t equals 7 years, t equals 18 years, and t equals 110 years. So f of 7, just plug 7 in for t. We should get about 370. F of 18, we'll get about 629. And f of 110, will be about 2,446. So when will the population of deer reach 760? Usually how we do a problem like this is we just know, well, our population of deer is the output. So we'll set our equation or equal to 760. And we'll have to solve for t. This one's kind of tricky. First of all, t is in the denominator. We'll have to multiply by t to get it out of there. And that will result in 760 times 0.0075t. plus 4 equals 50 times 2t plus 16. Okay, now let's distribute the 760. We get 5.7t plus 3040. Now we'll distribute the 50. We'll have 100t plus 16 times 50, 800. Next, let's subtract 5.7t from both sides to get all our t's together, and subtract 800 from both sides to get our constants together. Simplifying each side here, we get 2240 equals 94.3t. Divide by 94.3. And that tells us that t equals 2240 divided by 94.3. $23.754. So when will the population of deer reach 760? About 24 years after the deer are introduced. By introduced, I mean those 125. Now the research team's model predicts that the total number of deer that can be supported by the 150,000 acre area is limited. What is the maximum number of deer that the research team expected the 150,000 acre to support? To solve this question, just think about what's going to happen as the time goes on and on and on and on. If it just keeps growing, if the time goes on forever, then what's going to happen to the deer? Are they going to keep increasing forever? The researchers seem to think not. There's going to be some maximum number of deer that we can't exceed. You could graph this function on your calculator and scroll to the right and see what value the function is approaching. You could type this into your calculator, use a table, or you could just plug in really huge values of t, see what happens. I'm going to try plugging in really huge values of t. So 50 times 2 times, let me use 1000 plus 16 divided by 0.0075 times 1000 plus 4. That is 21,221. That doesn't make sense, because I accidentally put 100 instead of a 1,000. Let me try that again. 8765.22. Then if I, let me just jot that number down. If I plug 10,000 into that function, I get 12668.4. Now if I plug in 100,000, I get 13263.7. Let's go to a million. $13326.3. Notice that the number is starting to level out. Let me add another 0. 10 million. 13332.6. If we keep going up, we're going to get we're going to approach 13333.3. We're just going to get closer and closer to this number. Now we could have actually seen that originally. If you take 50 times 2, that would be the coefficient of t in this one, that's 100. Divide by the coefficient of t in the denominator, 0.0075. You get about this number here. The ratio of the leading coefficients will always give us the horizontal asymptote. So the deer will never exceed 13,333. Number 4. Given that f of x equals 1 over x minus 8, answer the questions below. Okay, so if x is 100, x minus 8 is 92. X is 10,000, x minus 8 is 992. And here we'll have 999992. Okay, so 1 over x minus 8 will be 1 over 92, which is 0.0109. This will be 1 over 9992, 0.0001. And 1 over 999992 is 0.000001. So notice that as the inputs get larger and larger, the outputs approach 0. So how do the output values of f change as x increases without bound? They decrease and approach 0. That tells us we have horizontal asymptote at 0, y equals 0. Here, negative 100 minus 8 is negative 108. This would be negative 10,008. Negative 1,000,008. And if we divide those, 1 over each of those values, we get some really small numbers. We're again approaching, we're getting closer and closer to 0. So how does the output value of f change as x decreases without bound, as x approaches negative infinity? It actually is increasing, approaching 0. We're getting less negative. Use a calculator, graph f, explain how the graph supports your solution above. So I drew this graph in the previous lecture, but notice what's going on here is as we approach infinity, this line is going to get closer and closer to 0, and if we approach negative infinity, if we decrease without bound, we'll get closer and closer to 0 also. So there is a horizontal asymptote at y equals 0. Number 5, given that f of x equals 3x over x plus 4, complete the following tables. So 3 times negative a million, it's negative 3 million. 3 times negative 10,000 is negative 30,000. This one will be negative 300. 300, 30,000, and 3 million. The important thing to notice is that as x approaches 0, 3x approaches 0, and as, from either side, from the left or right. Okay, then our denominator here, x plus 4, This will be negative 999,996, negative 9,996, negative 96, 104, 10004, 100,004. I don't notice a whole lot here. As x approaches 0, this one becomes, I guess it's becoming closer and closer to 0, but it's negative, and same thing here. You can also see that as x increases, both of these are increasing without bound. Anyways, what happens if we divide this number divided by this number? I'm going to go ahead and fill out this table. This column is much more interesting. If we look at as x decreases without bound, f of x approaches 3, and if x increases without bound, f of x approaches 3 also. So that's our signal. We have a horizontal asymptote at x equals 3. So what do you notice as x increases without bound? F of x approaches 3. What do you notice as x decreases without bound? Same thing. I guess we should answer these questions. Why does this happen? Let's see. So first, as x increases without bound, as x gets bigger and bigger and bigger here, these values get closer and closer to 3, but why would that happen? Notice that the ratio of these is always pretty close to 3. Notice that it's not quite 3 because of this 4 here. 300 divided by 100 would have been 3, but 300 divided by 104 is not 3. Same thing here, but as x gets really big, this 4 doesn't really matter. It's kind of like we essentially have 3x over x as x goes to infinity. This is basically what we have. The 4 doesn't really matter. So that just equals 3. This ratio approaches 3 as x goes to infinity. So that's kind of an explanation for each of these. And then we could use a calculator to graph the function. See, I don't have a lot of room to do this. So notice, again, we have our vertical asymptote at -4, but at y equals 3, we have something different happening. The function is approaching this line, but never quite reaching it. So that's our graph, and we see that as x increases without bound, the output approaches -3, and also as x decreases without bound, the output approaches 3. And we have a horizontal asymptote at y equals 3. Horizontal asymptote is a horizontal line that we draw at a value of the output. We draw at a value of the output when the following behavior occurs. Let a be a real number, f of x approaches a as x increases without bound, and or as x decreases without bound, then f has a horizontal asymptote at y equals a. Here we had one at y equals 3. In problem 1 above, a horizontal asymptote occurred at c equals 3.90. In problem 2, a horizontal asymptote occurred at r equals 0. Where did the horizontal asymptotes occur at 3, 4, and 5? We've already mentioned these. Notice I used n for the number of deer, and then y equals 0 and y equals 3 for 4 and 5. For some reason the book got 8,000 for the deer problem, but unless I copied the problem down wrong, I think that's a typo. There are two ways to determine horizontal asymptotes. The first method is to use a table or graph to examine what happens to the output values of a function as x increases and decreases without bound. Second method uses the formula of the function and compares the long-run behavior of the polynomial functions that make up the numerator and denominator of the rational function. The basic reasoning goes like this. Consider the polynomial function p of x equals x plus 5. When the magnitude of x gets very large, the plus 5 portion of the function rule is a proportionally smaller and smaller part of determining the final value of the expression x plus 5. For example, when x equals 20, p of 20 is 25. When x is 1,000, p of 1,000 is 105. When x is 100 million, the p of 100 million is 100 million and 5. And we can say that as x increases without bound, p of x approaches x. There's not much of a difference between these two numbers. So the larger these numbers get, the closer these two numbers are going to be, because the relative size of x plus 5 and x are nearly identical when you get really large values of x. We're saying relative of size. They're pretty close together. So as x increases or decreases without bound, what happens to the value of the expression x squared minus 10? In either case, the expression increases without bound. It's not a rational function, it's a quadratic function, a quadratic polynomial, and if you plug in x, if x gets larger and larger and larger, x squared gets larger and larger and larger, and you're just going to increase without bound. Same thing for negative x. If you plug in a negative value of x, you're just going to square and get a positive, but you're still going to see that we're going to increase without bound. The book says that x squared minus 10 gets closer and closer to x squared, which is true. I'm just going to read this explanation. So if you look at a table of those values, you can see that the ratio of those values approaches 1 as x goes to positive or negative infinity. And if you graphed the two functions, you'd see that if you zoomed out, eventually it'd be hard to notice a difference between them. Let's see. As x increases or decreases without bound, what happens to the value of the expression x cubed minus 4x squared? And why does this happen? So what happens is that x cubed minus 4x squared approaches x cubed. Pretty much as x gets larger and larger, this second term, because it's much smaller than the first, doesn't contribute as much to the overall value of the function or output. So the best way to do it is to graph both of them and keep zooming out, and you can see that at the end behavior of the functions, they look pretty close together. Number 8, using the reasoning from above, consider the function f of x equals 5x plus 2 over x squared minus x. As x increases or decreases without bound, we have 5x plus 2 approaches 5x, and x squared minus x approaches x squared. Therefore, the function would approach 5x over x squared, or 5 over x, as x increases or decreases without bound. If f of x approaches 5 over x as x increases or decreases without bound, then we reason there must be a horizontal asymptote at y equals 0, since g of x equals 5 over x has a horizontal asymptote at y equals 0. Use this reasoning to find the horizontal asymptotes for the following functions. So for these, you could use your calculator, use the table, see as x gets larger and larger, what happens to the output of this function. You could note that as x goes to infinity, 8 over x plus 1 to me it's obvious it goes to 0 because this denominator will get larger and larger while the numerator stays 8. So we're just going to be dividing by larger and larger fractions, larger and larger numbers, which gives us smaller and smaller fractions. We're going to go to 0. So the horizontal asymptote is y equals 0. Here I look at the ratio of the leading coefficients 1 over 2. The horizontal asymptote is y equals 1 over 2. You could note that as x goes to infinity, x over 2x minus 8, that minus 8 won't really matter. We'll sort of, like this value will approach x over 2x, which is 1/2 if you divide x by x to get 1. Let's see, over here it might be helpful to just FOIL out that denominator. Let's see, 2x squared minus 2x minus 3, I hope that's right, which is 6x squared minus 24 over 2x squared minus 4x minus 3. And as x goes to infinity, these terms won't really matter over here. We'll just have 5x squared over 2x squared, which means our horizontal asymptote is 5/2. Pretty much the ratio of this function approaches, I'm sorry, that's not a 5, that's a 6. 6 over 2, or 3, y equals 3. The ratio of this function approaches 3 as x goes to infinity, or negative infinity. Let's see, this one, just note that this will pretty much behave like x over x squared, which is 1 over x. And that means our horizontal asymptote is y equals 0. Notice that as x grows, the denominator will grow much quicker than the numerator will be because the denominator is squared. And so we're just going to get closer and closer to 0 again. This one, there's no horizontal asymptote because this numerator will grow much quicker than the denominator. Like if you want to use the same reasoning that the book recommends, this approaches x to the 5th over x cubed, or x squared, which is x cubed. And as x goes to infinity, x cubed goes to infinity, so it's not going to level off anywhere. This one we can rewrite as 2x plus 6. Actually, we can just cancel out the x plus 6. And we'll get 2. So this one, the ratio is going to be 2 no matter what x is, so y equals 2 is a horizontal asymptote. Number 9, generalizing the reasoning above, any polynomial expression p of x equals a n x to the n, etc. will behave increasingly like the first term as x increases or decreases without bound. Therefore, this rational function will behave more like this function as x increases or decreases without bound. What conditions are necessary for a rational function to have a horizontal asymptote at y equals? If we look at all of our functions up here, we had y equals 0 in this case and this case. The pattern is that the degree of the numerator is always smaller than the degree of the denominator. So if we want to have a horizontal asymptote at 0, then the degree of the numerator, n, must be smaller than the degree of the denominator. Or you could say m is greater than n, same thing. If you do not have a horizontal asymptote, the degree of the numerator is greater than the degree of the denominator, like this one here, because the numerator goes to infinity quicker than the denominator, so the whole function goes to infinity. And what conditions are necessary for a rational function to have a horizontal asymptote at y equals a? Note we always got some number here when the degrees of the numerator and denominator were the same. Like here the degree is 1, here the degree is 2, here the degrees are each 1. And in those cases, our degrees are the same, n equals m. And then the horizontal asymptote is y equals the ratio of the leading coefficients. If these are the same, they'll cancel out. We just have an over bm. Okay, that's a big idea. There's lots of symbols there, but look at some examples and think about how that works. This will come up again later, especially in calculus.